All right, how's it going, everybody? We are here today is Friday, April 2nd that I'm making this video here. And today we're going to be starting chapter 10. The kind of exciting thing about today is that this sort of represents the sort of a transition in this course here. We spent all chapters 5, 6, 7, and 8 learning everything that we need to know about integration so that we can use integration in tons of really important scenarios. But what we're going to see now is that in chapter 10, we're going to look at some alternate perspectives from which to view our functions of interest in an effort to help make the integration a little bit simpler. And then in chapter 11, we're going to move on to a sort of different topic here, sequences and series, to wrap up the semester. So in a sense, we're sort of done with this whole massive, bulky idea of how do you do integration and why do you do integration, right? So our big takeaways so far from the semester, therefore, should be our sort of summary of what we've seen so far this semester is really two big things. Integration is really important. It computes like every meaningful quantity that's ever computed in science. And integration is super hard. There's no super straightforward things that we can do with it. When I say that, I mean we often need to find really special cases and often put a lot of effort into performing integration. It's not something like a derivative where you just do it based on a set of 4 or 5 rules. Integration has a ton of kind of very, very deeply difficult techniques associated with it. And it really involves, I mean, almost as much of an art style as it is a technical process here. So integration is really difficult, but it's something that we've kind of also identified the serious value of so far this semester. So we know we want to do it, but we know it's really hard. So our goal should be at this point now in our mathematical careers to try and find ways that we can mitigate this difficulty. I think that one of the things that we've been seeing here, and some examples I'd like to highlight right now, are some of the difficult integrals that we've done this semester were things like finding the perimeter of a circle, finding the area of a circle, finding the surface area of a sphere. A bunch of things that seem like they should probably be really easy because they're based on the easiest shapes that there are, circles and spheres, right? Um, and so maybe one of the things that you could think to yourself is, well, I kind of understand why it's difficult for us to discuss circles when our coordinate system is built to talk about rectangles, right? Our XY Cartesian coordinate system is really good for defining rectangles. That's why we build Riemann sums the way that we do, but maybe it's a little bit less suited for other types of functions. So what we're going to look at this week in chapter 10 and next week also in chapter 10 is we're going to look at 2 alternate ways that we can describe functions, either as a system of parametric equations, or to describe our functions in terms of polar coordinates rather than Cartesian coordinates. And what we're going to find is that when we do our calculus in those settings, there are going to be families of functions that are more well suited to being described in something other than the Cartesian coordinate system, meaning we're going to encounter situations in which performing integration associated with certain curves might be either very difficult or impossible if we try and do it in Cartesian, but might become very simple to do if we define it in a fashion that is more suited to that type of function. So that's what our parametric and polar equations are going to represent for us. By the way, when you guys go to take 50C next semester, Calc 3, you're also going to get cylindrical coordinates, which is sort of like halfway between Cartesian and polar in 3 dimensions. And again, the purpose of all these things is just saying, listen, some problems are only difficult because of the perspective from which you're viewing it. Maybe if we just change our viewing angle, the way that we define the same curve, just use a little bit different definitions, maybe the math gets to be quite a bit easier. And that's definitely the case. So one of the things that we'll be learning here in chapter 10, and big time, I would say much more so in Calc 3 in Math 50C, you guys are going to see that it often is meaningful to stop before you just jump into doing math and say to yourself, am I even in a good coordinate system to solve for the types of values I'm interested in association with these curves that are given to me, or planes in Calc 3, or surfaces? And so stopping for a moment to consider your perspective should sort of be your, like, one of your new, I like to kind of reference all of my step zeros in doing math, which is often things like state what you know and don't know, draw a picture, and now one of them for you should, and again, step 0 meaning the step before you actually do step 1. Now a new step 0 for you should also be consider your coordinate system. Are we even measuring this thing in a way that's going to be well suited for the type of idea that we're looking to consider here? And so chapter 10, we're going to get parametric curves, we're going to get polar curves, we're going to see how to do calculus on both of them. We're going to see that some scenarios that we've done earlier this semester in Cartesian that were very difficult are going to become very simple once we define them slightly differently here. So let's do it. So in 10.1 and 10.2 this week, we're going to talk parametric stuff. Next week, we'll talk polar stuff. That'll be all of chapter 10. The other exciting thing is that today we are straight up not going to do any calculus whatsoever. We're just going to define parametric curves, get comfortable using them. In 10.2, what we're going to do is we're going to go back through like everything that we've done in calculus with curves and redefine those definitions in terms of parametric equations rather than function equations, y equals f of x. So we're going to see derivatives, we're going to see integrals, we're going to see arc length, we're going to see surface area, all of these good ideas. We're just going to restate how we would do all these computations if our information was given to us parametrically rather than using function notation or rather than using a function equation definition, right? So what is a parametric curve? Instead of directly defining a relationship between x and y, we're going to allow x and y to be functions of other parameters. And in a most simple case, there's only going to be one underlying parameter. And I just want to say right now, when we say other parameters, it certainly could be lots of things. But this is one of those places where we're definitely helped, even if we're all not physicists here. All of you, I think, will benefit from thinking of this parameter controlling x and y as time. And there's a bit of a physics holdover here, and it's certainly the case that we can use parameters other than time to help us define our x and y values. But I think that in most cases, like the underlying analogy that you should have in your mind about what a parametric curve is really, really helpful for us to think of x being a function of time and y being a function of time. Both x and y vary as time varies, but that still is going to result in an xy point being plotted on a graph, but with an underlying dependence on t, on what I like to think of as time. But it's not, you don't have to think of it as time, but it's going to be really helpful. So when I think of parametric graphs, I think of the trajectory of a fly. And as I was preparing my notes, I ended up with a very good diagram. So I kept a handwritten diagram here instead of drawing one right now. But what I like to think about when I think of parametric things is just where is a fly in space? And what I know is that a fly is going to zip around in front of my face depending on time. And at one given time, I'm noticing that there could be things, for example, you should notice a couple things that should probably bother you about this graph that I've drawn right here. One, this graph clearly does not pass the vertical line test. But that is no longer an issue of being well defined for us as it is with typical functions, because what I know is that, for example, if I look at this vertical line right here, I can see that there are 3 different places that our curve hits this vertical line. That's not really an issue of ambiguity for me here, saying, oh, well, if I know the y value, or I know the x value, how can I ever know which of the 3 y values I want? Well, 3 of these places are occurring at different times. It looks like this one is very close to the initial time. And then the second time that we pass through that x coordinate, we're getting to this bottom one down here. And then the third time t, at which we're passing through this particular x coordinate on some vertical line here, would be the middle passing through right there. And I can really easily see that. So I'm saying here, it doesn't matter if our parametric curves pass the vertical line test, because we're no longer thinking of y being dependent on x, and therefore there needing to be one y value for every x value. We're thinking of both x and y as being dependent on t, time. And therefore, there just really needs to be an xy coordinate for each of the times here. Now, you should notice here also that there is an overlap right here. It looks like we have passed through this same location at 2 different times. So even though this location has the exact same xy coordinate twice, those are occurring at 2 different times. So this might be occurring maybe at time 2 and then later again at time 8, perhaps, that we have achieved the exact same xy values right there. So it's still possible for me to distinguish between the 2 different pass-throughs of that location right there. Another interesting thing that you should note right here is that the slope of the curve is different at each of the 2 passing throughs right here. And so tomorrow, when we go to look at some calculus that's associated with these things, we will be able to do things such as prove that this parametric curve overlaps itself by showing that it has 2 unique tangent lines at a given xy coordinate right here. So we'll be able to verify that some properties like this may exist or prove that they don't exist for a given parametric curve when we go to do the calculus component of this in the next video. The other thing that's really, really important about this is that this is not just a curve in space. This is a curve with direction. This curve has a starting location and an ending location, and it traverses that curve in a ordered fashion right here. We are progressing along the curve in a direction. It's not just that the curve is one object, it is a trajectory that's traced out. And again, I like fight aggressively to make sure that I think of every single parametric curve as either a fly flying in front of my space or as a particle perhaps traveling along like a wire, like an electron on a wire or something like that that's experiencing outside forces or something like that, right? So it is the case that every parametric curve you ever draw in your life, it's going to have arrows on it that are pointing in the direction of motion that a particle or a fly is traveling along. Parametric curves are not just curves, they are directional curves. And that's really, really important here. So this is my like generic parametric curve right here. I obviously didn't give you any equations, but the point is we should think of them as being dependent on time. So we're going to be labeling time locations on our curves. They are directional, so it matters that we indicate what direction we are traveling as time increases. Notice that the direction of the arrows is just in the direction of positive time. All right. And my last thought here again is notice immediately the new flexibility that this gives us. It looks like we're now able to talk about equations that don't pass the vertical line test, whereas before that would make it very, very difficult for us to handle things like integration because we are dependent on a y equals f of x, which you can't write a y equals f of x equation for anything that fails the vertical line test. This would require two equations, right? It's just the x equals y squared graph I'm doing with my hand right here requires two equations. Y equals positive square root of x, y equals negative square root of x. It looks like maybe our parametric equations are going to be better suited to handle scenarios in which you want to have one x value be associated with multiple y values. But we have no definition problems here associated with that with parametric curves. That's nice. So what we're going to do is we're going to look at a whole bunch of examples here today. I'm going to give you a bunch of sets of equations. We want to see if we can come up with the graphs. We also want to do situations where I tell you the graph I'd like for us to produce, and we're going to see if we can come up with the equations that are going to be associated with that. And as usual, we're going to use our good buddy Desmos a whole bunch here today, since today is very, very much a graphical section. And every single time we do this today, I want you to stop and I want you to think about what this is like 50 years ago trying to do all this. I want you to think about that for every problem that you ever do associated with these difficult parametric curves and say to yourself, dang, I am super glad I'm taking this class when Desmos exists. And you should say that for every problem that you do for all of chapter 10. So let's look at our first parametric curves here. Some easy introductory examples here. So our very first example here, I'm going to define the function x and y both as functions of t, which I am always thinking of as time. In this case right here, I'm going to allow time to take on any real value. So we're going to go all the way from negative to positive infinity. So notice here that I am interested in drawing an xy graph, but importantly, x and y are both functions of time. And so the important first question that I always try to ask myself is, do I see any special relationship between the definition of x in terms of t and the definition of y in terms of t? And in this case, I definitely do. In this case here, I see a very, very simple relationship that looks like if you squared the x value, you get the y value. So it looks like for these two guys right here, I could make a statement that says something like y of t equals x of t squared, right? Or more simply, just y equals x squared, because that's going to give me t squared equals t squared. So the shape of this should be a parabola. But as we just said a moment ago, just describing the shape of a curve is no longer enough with parametric curves, right? What we also need to be doing is indicating things like direction, right? So here's my y equals x squared graph right there, but I'm going to do something wrong real quick just to do this once. This is now a terrible idea for you to do with drawing your curves. I spend a lot of time in algebra and math 30 yelling at people to put arrows on the end of curves when they belong there. They don't belong here because arrows are no longer indicating to us the graph continues on in this general direction. Arrows are now indicating to us a flow of time. So I need to go ahead and remove at least one of those arrows right there. And we should now ask ourselves, what direction should the arrows belong on this graph? And so here's what I'm going to do to help myself figure this out. I'm just going to identify a couple of time values here, right? So I'm just going to say at time 0, what are we getting here? It looks like x of 0, y of 0? Well, I can just plug in 0 into each of these equations. If I plug in 0 here for both, I'm going to get 0, 0. So I know that at time 0, I'm sitting right here at the origin. So that's going to be t equals 0 right there. And I could play the same game again, and we could say, all right, what's going on at time 1? And here, x of 1, y of 1 is going to be, if I plug in 1 for t into each equation, I'm going to get 1 and 1 squared, which is just 1 and 1. So it seems to me like I know that right here at 1, 1, this is me at time 1. So what I can kind of tell is happening right here is that to move forwards in time is to progress from left to right on the graph. So I feel pretty comfortable right now indicating the direction of motion. I can also pretty intuitively tell that we should be moving to the right across the entire graph right here. Hopefully you guys can see that this should be our location at time -1 right here. Notice that because my times were covering negative to positive infinity, it does make sense for me to account for negative time. This says, where would this particle have been 1 second ago? I can use these parametric equations to kind of help myself figure that out right here. So in general, our goal for our parametric equations when we're graphing things is to always ask ourselves if we want to graph this thing in the xy plane. That's really important. We're still graphing in the xy plane, even though our true underlying variable is now time, which we're not directly graphing. It doesn't get its own axis here. Is often saying to ourselves, is there some algebraic relationship we can see between x and y? If and whether we can or not, it's also often very, very helpful. Just like you guys know, I mean, think way back to like your first ever graph drawing that you did in any algebra class. If you don't know how to graph something, start plotting points. That's exactly what we did right here. The only difference is that here we also need points to help us out with things like direction of motion rather than just shape of the graph. But again, if we were unable to find some nice XY relationship right here, like y equals x squared, that might be a good situation for me to just go start plugging in some t values and plotting some points. See if I can generate a curve that seems like something I can vaguely recognize. Obviously, if I'm just plugging in a bunch of t points and I'm getting a graph that looks like this, it's not like I'm going to be like, oh, look, I plotted enough points and I got this squiggly crazy graph right here, right? Some of these might get a little bit hairy and we can't quite do this algebraically, but I'm always hoping when I see parametric equations that I can say to myself, is there any natural XY relationship that I can develop that no longer has dependence on t? So you should notice that we took a system of parametric equations and we sort of unparameterized it by finding the direct relationship between x and y, which is y equals x squared in this case. So for our second example right here, you should notice that this second example is almost identical to the first. The literal only difference is that we've introduced a negative right here. Now, it's still the case that when I combine, when I try to say to myself, hey, is there any relationship between x and y that we know? It's still the case that if you square the x term, if you square negative t, you're still going to get positive t squared. So it looks like we've maintained the relationship that y of t is going to be x of t squared, or just y equals x squared. So shape is still a parabola. It's still the same parabola, right? So the question is, do we get anything different here? So I know what my shape looks like. Oh, I just started drawing arrows on the end. Don't want to start doing that yet. So now let's again go look at some of our points in space and see where they are. So I'm looking at time 0 here. And at time 0, I can see that x at time 0 and y at time 0, well, they're still both just 0, 0. Right? Plugging in 0 for each of these gave me 0 for both. That's nothing exciting. If I go ahead and I look at time 1, what I'm going to see here is that x at time 1 and y at time 1, well, now it's a little bit different. When I plug in 1 for my x equation here, I'm actually getting -1. But when I plug in 1 for time for the y equation, I'm getting +1. So notice that the one thing that changed a little bit for us here is that now I have that time 0 is at the vertex still, but it looks now like time 1, +1, is on the left-hand side over here. So it looks like what changed here by changing positive t to negative t for my x coordinate is we've changed the direction of flow on this parabola here. So it seems like now, if I want to go from negative infinity to positive infinity, we're actually moving from right to left through this parabola rather than left to right. So again, this is changing the motion, or changing the direction of motion here. So if you're thinking about this as being a fly flying in front of your face, or a particle on a wire, or something like that, then it's now moving backwards relative to the first example that we did. So I might even go so far as to collectively say that examples 1 and 2 right here maybe represent a forwards time versus a backwards time trajectory for whatever the thing is that we're thinking about, a particle on a wire. So just negating our x-coordinate is a pretty standard way to kind of just flip the direction of all of our arrows right there. Cool, so very, very similar, but again, notice that even though these graphs have the exact same shape, they had different directions because their parametric equations were not quite the same as one another right there. So the direction matters. Those arrows matter. Don't go ahead and just stick your "and the graph continues on" arrows. We don't use those with parametric equations. We only use flow direction arrows with parametric equations. So now let's go ahead and let's look at our third example, and let's recognize that it is almost identical to the second example. But our one difference is I'm now no longer giving us an infinite time span right here. We're now looking at time going from -2 to +1 here. So what I already know about this graph is I already know that this graph is going to look like a parabola. I know that I'm going to get my y equals x squared relationship, but we're only doing this for a finite amount of time here. So what I want to do to myself, I think right here, is I think I want to know where we're at each of these two endpoints right here, so I can decide where does my graph start, where does my graph end. Notice that this is very, very similar to us being given a domain, but normally when I say, oh, the domain of this function, you think about a span of x values. Well, now we're giving a span of time values, so we're sort of like one step removed from knowing what our XY window is going to look like right here, but we can just do a bit of easy computation and find out. So let's do t equals -2, and now notice that time at -2 is technically not included here, so we're going to have an open circle rather than a filled-in circle, but it's still useful for me to know where that open circle is going to be located. So if I do time -2, then x at -2 and y at -2 appear to be at the location. Plugging in -2 here gives me +2. Plugging in -2 here gives me +4. So I'm at 2, 4 is where we start. And at time 1, we're going to get x of 1, y of 1, and that's going to be giving me -1, 1, and that's where we're going to end. All right. So I think I can go ahead and graph this guy now. I think that the easy things for me to do here, 1, I know only need the positive half because I'm graphing y equals x squared. 2, I know that time 0 is going to be down here at the vertex like it's been. I know that I want to go to -1, 1, right? Oops, I drew a closed circle right there. I want to draw an open circle. At 1, 1, this is my time 1. That's where we're ending, is right here. And I know that we're going to go on to 2, 4. This looks like my time -2 is located here at 2, 4. All right. Cool. So it looks like I know that my time, and again, I'm never done graphing a parametric curve until I've drawn my arrows indicating the direction of forwards time. Since this is my smallest time and this is my largest time, it looks like we're going to go ahead and progress in this direction right here. So we've only got a finite chunk of curve right here. So what I want to do now is I want to take a pause and let's go take a look and see what these guys look like in Desmos. I want you guys to be able to graph these in Desmos. This isn't really a difficult thing to do, but it's not the way that you think it is. Basically what I'm saying is you can't just type these two lines in Desmos and get this graph right here, which is a little bit unfortunate. I wish that you could just like indicate that you're defining something parametrically and take it in that way. Desmos wants to see this a smidge different than you type in other things, so I just want to show you guys now how this looks. So let's go ahead and try and produce this exact graph here in Desmos. The other thing that I'm going to tell you is that since Desmos is never going to put arrows on a curve, I pretty typically, if I'm trying to do like a good job of analyzing a parametric curve, I always graph it twice in Desmos. I graph it once to produce the actual shape of the curve, and then I graph it a second time to put a dot on the curve that will move in the forwards time direction. So the dot is going to give me my arrow information. So let's go ahead and do both of those things here. So in general, when we're in Desmos and we're trying to graph a parametric curve, the format in which we're always going to graph it is we can't just do x of t equals stuff. That's not going to work out like this. Instead, what we need to do is indicate this as an ordered pair like we've kind of been doing. In fact, Basically, the way that we've been writing this kind of stuff right here, this x of 0, y of 0, x of 1, y of 1, this is exactly the structure in which we need to give it in Desmos. We just want our x information, which is going to be negative t, and our y information, which is going to be t squared, given as an ordered pair in Desmos, and that's going to generate an entire curve for us here. So let's go ahead and do that. So again, our equation of interest here was our x was negative t, and y is t squared. And notice it gave me a little piece of a graph over there, but notice it only gave me the graph from 0 to 1. That's always going to be Desmos' default. So in our case, though, we had from negative 1 to 2. Or excuse me, we had it from negative 2 to 1. And I know that because our graph is backwards right here. Negative 2 to 1, right? Am I right? Yes, from negative 2 to 1 right there. It's got the or equal twos in there. I'm not too worried about that. I'm enough of a mathematician that I can disclude those endpoints on my own right there. But the thing that should be very dissatisfying to you is that although Desmos did come up with the appropriate shape of our graph, it does not indicate direction to us. And that's kind of an issue for me here. All right, so here's what I do to kind of fix this. Generally, as I said a minute ago, when I want to do like a really good job of analyzing my parametric equations in Desmos, I always do the exact same thing twice. Once I do a t, because Desmos recognizes t as a variable rather than a parameter, the next thing, and so it knows to like graph this parametrically specifically because you're using t. If I were to use a different variable like a, then Desmos now thinks of this as something that needs a slider bar. And it's now going to think of this as a point rather than a parametrically defined equation. So I'm going to add a slider for a. And now this is going to give me, ooh, and notice here, I think that I only want a, so I didn't want a to go this far because notice that a is representing t, and t never takes on a value of 3, so that's not cool. So here's what I'm going to do. I'm going to click in the box here, and I'm going to make sure that a also only goes from negative 2 to 1, and I'm going to hit enter. And now I can start over here at negative 2, and I can click play, and I can watch the direction of motion that our point should be traversing right there. Can I turn that off? I want it to go, oh, repeat in one direction. Hey, that's perfect right there. So it just goes back to the beginning instead of going backwards right there. And now we get some nice direction of motion right there. So the big lesson here is Desmos recognizes t as a special character, as a variable, versus things like a that it recognizes as a parameter, right? So therefore, it's often most practical to graph your entire parametric setup 2 times. One using the variable t so it graphs the curve, one using any other parameter over the exact same bounds, negative 2 to 1, so that it will put a point on there that you'll be able to see move in a given direction. This is also going to be really important because in our next couple of examples, we're also going to discuss things like the speed at which this point is moving right here. That's going to be something of interest for us, so we'll take a look at that in a second here. So at least this has verified for us what we thought we were going to see. We got the shape of the graph correct, we got our endpoints correct, and we got our direction of motion correct right here. So we kind of verified all of our components with this Desmos graph here. So let's pause this guy and let's pop back over into Microsoft Word and let's do a couple more examples. So obviously example 1, 2, and 3, really basic. Shape of the graph never changed. We just changed our boundaries and our direction of motion. Let's do some a little bit more exciting examples right here. So our next example, and I'm going to go ahead and say right now, I think that this is probably the single most important system of parametric equations for you to be able to identify that there is. If you were to ever recognize one system of parametric equations in the wild, this is the one. This is the one where you will maybe embarrass yourself if you don't know what shape we're describing like that we're looking at right here in the future. So this one matters. If you're paying attention to only one out of the like 8 examples we're doing here today, this is the one right here. All right, so x of t and y of t. And I'm going to ask myself the same questions that I ask on all these guys. And I'm going to say to myself, is there any known relationship between x and y? And now this is where I give you the crazy eyes and I say, do you know any equation that relates sine and cosine? And the answer is, yeah, you do, or else you wouldn't have gotten into this class since it's a prerequisite for it. And so I'm thinking to myself that sine squared of t plus cosine squared of t is equal to 1. That's something I just know. It's a Pythagorean theorem. I can prove it. I'm not going to because I proved it in trig class. You all have seen that multiple semesters ago. But what's much more important for us right now is that we're trying to come up with an XY relationship, not a statement in T. But the good news is that this is a known true statement relating sine and cosine, which I can then use to relate x and y to one another. So it looks like what we're really just saying here is x squared plus y squared equals 1, and therefore the shape of our graph is a circle. Now, you should notice that we haven't discussed our bounds yet. We'll discuss those in a minute, but it's certainly the case that they're not just infinite bounds, right? We have a finite system right here, but also these are like the most typical bounds that you've ever seen related to sine and cosine right here. So nothing too strange right there. So one thing I know now is that I know that my graph is going to be the unit circle, a radius 1 circle. Hey, it's not the worst circle I've ever drawn right there. Okay, so we've got our unit circle right here. And now, if we were just given the equation x squared plus y squared equals 1, we'd be done. But unfortunately for you, oh, well, no, fortunately for you, because this is really cool stuff here, we've been given parametric equations, so it still matters that we determine things like where do we start, where do we end, what direction are we traveling in here. So let's go ahead and do a few things here, like say, where is time 0? What's going on at time 0? We should be getting x of 0, y of 0 equals sine of 0, cosine of 0, which seems to be located at 0, 1. So that tells me that we're starting here at the top of the circle. This is our initial location. Now what I typically do is go find my ending location. So I'm going to do 2 pi. However, hopefully all of you guys are savvy enough with your trig to know that this is a foolish endeavor for me to go work this guy out right now. It's pretty obvious that we're still at the exact same location because sine and cosine are both periodic with a period of 2 pi, and therefore any input that's exactly 2 pi later than any other input is going to give us the exact same outputs again. So you should notice here that this is exactly our location at 0 and at 2 pi. So it looks like we both started and ended at that point right there. So it seems to me like it's not 100% clear exactly like what direction our motion is going to be. So I've got to pick some other time to help myself out with this. Now, here's maybe a thing that I'm thinking to myself. I know that as time gets ever so slightly larger right here, I know that our sine value starts at an x value of 0. And my question is, what's going to happen to our x value as this gets a little bit larger? As t gets larger, sine is going to go from being 0 to being some positive number. And it's also the case that as t starts at 0, cosine's at its maximum, it's going to get a little bit smaller. So I'm picturing to myself that this should be going to the right from this point right here, because I know that for small positive values of t, we're going to get positive values for both sine and for cosine. So it feels to me like we should be moving into the first quadrant right here. Another thing that you could do for yourself, though, is just give yourself a more useful point in space, like pi halves. By the way, notice that plugging in pi wouldn't necessarily be super helpful because it's perfectly symmetrically opposite here. So it wouldn't be clear to me if I went that direction or that direction to get to it. So I'm picking like a point that's not symmetric with this point right here to kind of help myself get a little bit more sense of it right here. So if I did x of pi halves and y of pi halves, I'm assuming that I'm making a quarter of the distance around the circle, and the question is in what direction. Sine of pi halves is 1. Cosine of pi halves is going to be 0. And we get 1, 0. So I know that at time pi halves, I'm sitting right here. So this is just further evidence that we are, in fact, traversing the circle in the counterclockwise direction. And it looks like we did exactly 1 lap. We started at the top and we ended at the top. So this is exactly 1 revolution, 1 counterclockwise revolution around the unit circle. Starting from 0, 1. so this is my full description of what I'm seeing right here. Notice that I gave the shape of the graph. I gave the direction of motion. I gave the starting and ending location. I gave the total amount of travel that occurred, right? All of these things are like relevant descriptions overall to this parametric equation right here. We're no longer just looking at just the shape of a graph. We're picturing a motion of a particle, right? Or of a fly in space. So again, I think the big thing to get over here with these parametric equations is just because you know that the parameterization of x being sine and y being cosine makes a circle, there's still kind of a lot of other stuff to say. Where did you start? What direction did you go? For how long did you do it? Those are all other questions that are needing to be answered to fully describe the parametric equations at hand here. So the question now is for number 5 is how does this change when we now do 3t instead of 1t? And all I'm going to do is a real simple little bit of algebra to kind of modify this a little bit. And so what I'm seeing here is we were told that time was going to go from 0 to 2 pi, but I am, sorry, let me get my mouse back here. We were told that time is going to go from 0 to 2 pi, but I'm no longer interested in just describing t. It looks like 3t is, in a sense, my parameter of interest, my variable of interest there. So what I'm going to do is I'm going to multiply this whole equation by 3. It seems, I got so excited to write the pi that I wrote pi instead of writing t where it belongs right here. So I just multiplied this whole inequality by 3. And notice that what this is kind of telling me now is it seems like the arguments going into sine and cosine are going to span all the way from 0 to 6 pi. So it seems to me like this should be the exact same graph, but the only difference should be is it looks like we're going to take 3 laps instead of just 1 lap. So should be same shape, starting point, ending point, direction of motion, but we'll take 3 laps. Now, I do want to say one other thing about this. One other thing I could say to you is, how else could we have taken 3 laps around this thing? What other modification could we have made? So one thing I want to compare this to is, what if we had just left this as sine of t, cosine of t? What else could we have done? Well, we could have just done 0 to t to 6 pi. Notice in that case, what that's saying is just do this for 3 times longer. So if I wanted to take 3 laps around a track instead of 1, the 2 ways I could do it is I could either run for 3 times as long, or I could run for the same amount of time but run 3 times faster. And that's what we've got going on here, right? So we're gonna travel 3 times farther by traveling 3 times faster rather than by traveling for 3 times as long of time, right? So we're still gonna get this same shape right here. But maybe my question to you now should be, what are the times that we reach that we pass through the starting spot? So here's our unit circle, and I know that I'm starting here at time 0. But notice our total time is only going to 2 pi, right? But what I now know is that we only need to input a third as much to get to 1 full lap around. So 1/3 as much of 2 pi should be 2 pi thirds. And you should notice that when I plug in 2 pi thirds here, 3 times 2 pi thirds is just 2 pi, which has brought us back to where we started. Similarly, at 4 pi thirds, that's just like having taken our next lap around right there. And finally, at 6 pi thirds is just the same thing as 2 pi. So that's the 4th time that we'll hit that spot, completing our 3rd lap around this thing right here. So we're still getting all of our same direction of motion. It's still a radius 1 circle. but we're taking 3 laps because we traveled 3 times faster, not because we traveled for 3 times as long. So importantly, 3 times further, not by traveling for 3 times as long. But by traveling 3 times as fast. So I want to go ahead and make that comparison in Desmos right now. Again, this multiplying by 3 is not affecting the duration of time for which we're traveling. It's affecting the speed at which we're traveling here. So let's go ahead and take a look at comparing these in Desmos. And what I'm really going to do in Desmos is I'm going to let this 2 pi right here be 6 pi so that they're both going to take 3 laps, but you're going to see that this one's going to take us 3 laps in 1/3 of the time right here. So let's go ahead and compare these two in Desmos. So I'm going to come over here and I'm going to do my sine of t. Oop, I guess I should switch to Desmos probably, huh? Sine of t and cosine of t. And so remember the one I'm modifying right now, I'm not too worried about the bounds on this one in that I just want to get the graph of the circle to be visible. There's my graph of a circle, great. Now what I really am actually interested in is seeing 2 different sets of dots appear on this thing here, right? So I'm gonna get rid of that for right now, although I don't know that I need to do that. Okay, so what we're gonna do here is we're gonna do sine of A and cosine of A. I also want to do sine of 3A, cosine of 3A. Let's go ahead and add this slider for A here. And what we want to see is that when we start at time 0, they're both at the same place. But what you should see is that as we move, one of them is moving 3 times faster than the other. So there's 1 lap completed for green. Notice that the blue dot is only at 1/3 of a revolution. There's 2 laps completed for green, and the blue dot is at 2/3 of a revolution. And there's 3 laps completed by green, and the amount of time that it took blue to complete 1 single lap right there. I feel like this maybe would have been nicer as like a 0 to 2 pi right there. I wish that would play like a little bit more continuously. Oh, it's doing that stupid thing again. One direction. Okay. And there we go. We can see that one of our dots is moving 3 times as fast as the other dot. Man, I wish they would do that a little bit slower right here. Let me slow that down. There we go. A little bit more visible right there. Boom. And they intersect right up there at that one time, right when they start right there. So notice here in this case, one of the other things that's kind of worth considering in a parametric equation is it's definitely not the case that our particle is moving at the same speed at any given location. It might be, if we're going from here to here, that we move lightning fast the first 90% of it, and then we take a really, really, really long time to go that last 10% out there. The speed of the particle is another thing that's very difficult to judge when we just state parametric equations, but gets a lot simpler for us to identify when we can look at these handy-dandy graphs in Desmos. And so now let's all say it together. Man, I'm glad I'm taking this class in 2021 when I have Desmos to help me visualize these things out here. Imagine doing all this 50 years ago. Or don't, because it makes me sad. All right. So good comparison, these two. Speed of solutions. The particle is moving 3 times faster in order to travel 3 times further rather than traveling for 3 times as long. And I know this because my parameter that's being controlled here was the same amount of time, 2 pi units of time for both of them. So they both traveled for 2 pi seconds. One of them traveled 3 times as far as the other one, so it must have been traveling 3 times faster. Very cool. All right. So let's see our next example then. All right. Here we are. Something a little bit different. Now this one's going to be a ever so slightly more challenging in that I want us to come up with like a good sentence, or even it's almost going to be like, well, it's going to just be one long sentence right here. But the point is, we're going to come up with a graph that's a little bit harder to meaningfully draw as a full descriptor right here. And like even like this one right here, you should notice that here it's a little bit weird. Like I don't really think it's easy to state graphically that 3 laps are going to end up getting taken. It's even a little confusing because technically there's 4 points right here, but those are sort of like our 4 fence posts to build 3 pieces of fence, right? To take, if you're going to take 3 complete laps, you were really at your starting point 4 times because you started there and ended there. So really maybe like this sentence right here in the box, this is sort of what I'm looking for us to come up with for the next one, because the next one's shape is going to be like this, where it's like, I can sort of draw it, but I can't really draw it well enough, so you kind of need a sentence to help you describe it a little bit. So let's describe the motion of a particle that has a location defined by these parametric equations. And super importantly, you should notice that I didn't describe to you any t bounds. This sort of says to me that there's no restriction on t, but that's sort of like left off vaguely right here, right? So we'll have to figure that out for ourselves once we kind of get a handle on what's going on right here. So I'm going to ask the same questions I always ask. Do you see any algebraic relationship between x and y? And I think I see a really simple one again right here. In fact, it's the one that we've seen already multiple times right here. It looks like we're going to get some version of y equals x squared. So I think that I know that this is my general shape, but there's something that I'm thinking that's like a little bit different about this right here, is that this isn't just going to just be the parabola y equals x squared. My question to you is, what values could x take on and what values could y take on? And you should notice that because they are defined by trig equations, there's going to be a pretty limited span of values that x and y can both take on. Let's ask about that. Since x of t is sine of t, I know that it has a range of -1 to 1. That says I know the outputs that we get from the sine function are -1 to 1. On the other hand, I know that y of t is sine squared of t, so I'm going to square all of the outputs that I'm getting from the sine function. And I know that squaring things makes stuff positive, so it seems to me like sine squared should only have a range from 0 to 1. So what this is going to say to me is it seems like we're going to get this parabolic shape, but it seems like my x values are stuck between -1 and 1, and my y values are stuck between 0 and 1. So I feel like we're going to be living in a box that looks like this. Right, there's my 0 to, wow, I did a great job with my box right there. I'm going to mess it up with my parabola. Hey, not bad overall right there. Great job, Tony. So it looks like there's my -1 to 1 and my height of 1 that we're getting right there. So what's not at all obvious in this problem is that we're stuck in this box. We had to stop and like kind of think about that a little bit right here. And again, remembering that just because you've come up with an algebraic relationship between x and y, we can't just straight up discard all of our information about t. It's still providing us really useful information, such as the spans of values that our x and y values could ever possibly take on here. Here I know that x and y will never be outside of these spans, so it's not possible that more than this of the parabola is ever going to get traversed, right? So the interesting thing here is that even if uh, t is in the interval from -infinity to +infinity, we still get a finite graph, right? So, just other things that are not really weird once you get used to dealing with parametric curves, but might feel a little bit odd at first that we can travel for infinite time on a finite graph. So my question is, where and when, right? Like this is, hopefully you're all in agreement that we're not done drawing this graph because there's no arrows on it right here. So I want to kind of stop and now say, like, where do we start? Where do we clearly don't really end anywhere. Where are we at time 0? Where are we at time pi halves? At pi at 3 pi halves. I'm going to throw in values that I know are really easy for me to compute right here so I can get a handle on where we are on this graph right here. So let's go ahead and draw ourselves a better version of this. And I'm just going to draw a bigger one just because I know that I'm going to need, I'm going to be marking some times next to some things right here. So let's go ahead and evaluate some of these guys right here. So time 0, then I'm going to be getting x of 0, y of 0 is sine of 0, and sine squared of 0, so that's 0, 0. So we've got our first mark on the graph right here, which is that time 0 is down there at the bottom. And now I'm going to go just, and again, I'm just picking trig numbers right here. So whatever's easiest for myself. X of pi halves, y of pi halves. Well, I know that sine reaches its maximum at pi halves right here, right? So I'm going to get 1 and 1 squared. And so it seems to me like we're going to be in this upper right corner by the time we get to pi halves. Next up, we should graph what's going on at pi. And so, by the way, it seems like we started here and swung up into the upper right-hand corner. But what's about to happen right now? Well, at pi, we're back to 0, 0 for sine and for sine squared. So it seems like the way that this graph started with, or excuse me, the way this particle started is it started at the bottom, it moved up to the upper right, and then it went immediately back down to the bottom. Where are you guessing it's going to go now? Let's go ahead and take a look. Three pi halves. The 3 pi halves getting a little scrunched in there. 3 pi halves is pointing down, and so I know that sine is going to be -1 there. But when I say sine is -1, we're still squaring it to get 1, so that's going to put us over here for 3 pi halves. I forgot my t on this other thing. I don't just want to write pi halves right there. Let me write t equals pi halves. And where are we going to be next? Well, I think that you guys, since you know trig, know what's going on here. If I now do 2 pi, I should certainly be at the same location as I was at 0. So it seems like we're going to be back here at 2 pi, and then back here at 5 pi halves, and then back here at 3 pi, and then back here at 7 pi halves. And so notice that it's really difficult for me to appropriately place arrows on here because we start at the bottom at the at time 0, and we go up, down, up, down, up, down. It looks like we're just rocking back and forth forever sitting on this parabola right here. So the problem is that we spend just as much time going in one direction as we do going in the other direction at every point on this curve. And so it's maybe a little bit less sensible for me to draw arrows here. And it's not even just that we travel in both directions. We spend the exact same amount of time traveling in each of the directions right there. So one way that we can mitigate this is to try and draw some time labels on here like we did. I think a very careful reader right here, as long as you know your fractions and in what order they go right here, you could see time 0, pi halves, pi, 3 pi halves, 2 pi, 5 pi halves, kind of see that rocking back and forth motion here. But that's why I think it's a useful thing for us to do to just maybe type out a statement right here and say where we're going to go here. So I think that we're going to start at 0, 0, travel to upper right corner, back to 0, 0, travel to upper left, So I think kind of verbalizing, like it rocks back and forth, right? And so let's go ahead and take a look at this one in Desmos, since this one's a little bit weirder than the other ones right here. But again, this is one where I would say that there is literally not a way for me to just draw the graph and it do a full description job right here. This is just one where you just need to give a little bit of a sentence or else it doesn't quite make sense what's happening here. So let's go ahead and throw this guy in Desmos. Let's give it this infinite time duration right here, or at least I'm going to do time from like 0 to 100 or something like that. So we'll see it rocking back and forth. So our two equations are sine and sine squared. Let's go ahead and do it. So over here in Desmos, we're looking at sine and sine squared. And again, all I really need is 0 to 2 pi to be able to see the whole thing. Notice that if I make this like 10 pi, it doesn't help us. It doesn't like get us more parts out there. That's just to draw the curve itself. The thing where the time actually matters is on the parameters down here that we include. So I can get rid of that one. I can change this one to sine squared. And now I'm going to go ahead and I'm going to click this before I go here, and let's just make this like 50 pi or whatever right here. And let's go ahead and see a nice and slow animation right. Well, okay, not that slow, but point is we can see it doing this smooth rocking back and forth between our 2 points right there. Maybe I could have made this like way more reasonable right here. Okay, now I go ahead and play it. Now it's going to rock back and forth in a way that we can actually see it right there. So again, I think that this just requires a verbal description. I don't think that there's any way for me to purely graphically indicate this type of thing. But, you know, I feel like I've sort of shouted at you guys a little bit about this earlier this semester when we did our numerical solutions here. This is sort of one of those things where I don't feel like static descriptions of things are really what's going to be happening in the future. I think that in the future, we are going to be expecting for people to have like interactive code to deal with for solutions for things, to where I can literally see objects move, and therefore that's just as good as a sentence to me. And so, I don't know. I like the incorporation of technology here, because now I don't need a sentence if I can see the dot moving, right? So this is good. This is validated exactly what we thought was going to happen right here. I feel pretty good about this guy. So let's pause this. Let's go back and take a look at our next exciting example here. Yeah. So now we got two left here. One, we're going to build our own parametric equations to build a desired directional graph. The other thing that we're going to do here is we're going to talk about intersections versus collisions, and that'll be our last example here. So let's go ahead and construct our own parametric equation. So we have been given a description of something we would like to graph, including directions of motion and total number of cycles. And so what we want to come up with is what are our x of t and y of t equations that we think that we want to build. So we're going to do this sort of progressively. What I'm going to do is I'm going to state an equation that's sort of right for one piece of information, and then we'll add information. This is one of those things that's really hard to just write down an answer, right? So I'm going to sort of progressively build this. So we want to determine parametric equations that describe the path of a particle. It's going to travel around a circle, and so as soon as you see circle in parametric equations, you should be thinking sines and cosines. This guy's going to have a radius 2, so that's going to change a little bit. We're going to go in the clockwise direction. We want to make sure our directions are correct. We need to make 2 laps. We want those 2 laps to occur in 1 second, and we want our starting location to be 2, 0. You should notice that 100% of this is stuff that we have already discussed here today, except for radius, and that part's really, really easy. We just need to play around with this a little bit to get our pieces right here, okay? So this is definitely a trial and error thing, but you guys kind of have a feel for like where you should be trialing and erroring, right? I mean, we know like what things to maybe adjust to make some of these things happen, and this is just one of those things where it's like, you should stop and take a minute to say to yourself, you know what, there's not really that many things I could modify to try here. Like this isn't going to be like some big monumental trial and error effort right here. We're going to guess a few things, and they're either going to be right on the first try or they're going to be right on the second try pretty much across the board right here. So this isn't going to be too terrible. So what I'm thinking here is this. We've got to deal with the fact. So I'm just going to state a bunch of facts. Circle, radius 2, clockwise, 2 revolutions, 1 second, start at 2, 0. These are the what's this, 6 conditions that we need to meet for our parametric equation to be legit. So let's kind of say what we know. Circle. What does circle mean to me? It means to me sines and cosines. Now, you should notice that one of the very important distinctions that we should be making right now from our example up above from the circles is that, for example, I could have swapped the sine and cosine equation right here, and most all of our results here would have been the same. It certainly still would have given us a circle, in this case a unit circle, because sine and cosine each had coefficients of 1. So I'm thinking to myself, we still want sines and cosines, so I'm still thinking of something like cosine of t and sine of t, or something like, or like I don't really know, right? So let's make our first kind of guess right here. One thing I know is that I really want 2 sine t and 2 cos t, right? That's going to give me our radius term. We know that like x equals r cos theta, y equals r sine theta. We've learned those things in trig class. So I'm just sticking my radius term where I think my radius term goes. So now I'm going to make my first sort of guess right here. And this, I don't think that this guess is like my final answer. I'm just trying to like put some stuff down on paper here. So how about this is 2 sine t and y of t equals 2 cos t. So I'm sort of just guessing some stuff right here, right? Let's see if this agrees with some of the information that we've got. If I were to do this, then we would take, for example, maybe we can say at time 0, where are we at? Well, x of 0, y of 0 is going to be, when I plug in 0 here, I'm going to get 0 and I'm going to get 2. And notice that we were looking to start at 2, 0. So my first thought right here is we should maybe switch the ordering that we're writing these in. So now I'm going to make my new guess. And let's let x of t instead be the cosine part. And let's let y of t be the sine part. So with this equation, I think that I'm getting a circle. I think it's got radius 2. I think that we're starting at the correct location. Confirm that real quick. When I plug in 0 into the x equation here for time, I am in fact getting 2, and I am in fact getting 0. Sine of 0 is 0, so this looks good right here. So what's the next thing that I want to check right here? Well, one thing that I know is that we're not with time. The 2 revolutions depends on time, right? And we haven't started talking about our time interval yet. And the 1 second thing, and doing this is like our speed. This is telling me how long it's going to take, so it's going to affect our speed. That's probably going to affect us playing around with the interior components here, like cosine of something t. And I haven't started messing with those things yet. So my next question is this clockwise? Is that our direction of motion right here? So I guess I need to draw myself a little sketch of this guy here. It looks like we're starting at 2, 0, so we're starting out right here. And what I typically then would do is just plot a point slightly further into the future right here. So let's go ahead and do t equals pi halves. And if I do that, x of pi halves, y of pi halves. So plug in pi halves in for x. Cosine at pi halves is 0. Sine at pi halves is 1 times 2 is going to give me 2. So it seems to me like this is my t equals 0. This is my t equals pi halves. So it seems like we're traveling in the counterclockwise direction. So it seems like we are not quite right with this guess either, because this is going counterclockwise. I tested 2 points, saw that our direction of rotation was counterclockwise, and so we're going the wrong direction here. So now this is a little bit weirder because what we need to do is we clearly need to make like an opposite type of change because I want to go in the opposite direction. But what we need to not screw up is we need to not screw with where we started, right? We still need to remain at 2, 0. So what is a way in which I can negate something while still leaving this the same? And you should notice that if I negate my cosine component here, then I would be starting at negative 2, 0, and I don't want to do that. But you should notice if I negate my y component, the negative of 0 is still 0, but what that will do is it will put our time at pi halves down here at the bottom instead. And so I think that that's going to maybe fix our clockwise direction. So my new guess is going to be x of t equals 2 cos t, and y of t is going to be negative 2 sine t. I'm still getting a circle of radius 2. I can now confirm that at t equals 0, we're still going to be, when I plug in 0, I'm still getting 2 and 0. Now when I plug in pi halves, I'm now plugging in pi halves and I'm getting 0 and negative 2. So now we started at 2, 0 at time 0. And now at pi halves, we're down here. So now I feel good that we are, in fact, going in the clockwise direction. So we've got a bunch of our components correct so far, right? We've got the circle, we've got the radius 2, we've got the clockwise, we've got our starting location. It looks like the last thing we need is we need to do 2 revolutions in 1 second. So what that means to me is that we need to do 2 laps in 1 second, all right? So when I see 2 revolutions, excuse me, sorry, let me back up right here. When I say 1 second, that says to me that we need our time interval to go from 0 to 1. That's all I'm really saying for the 2 seconds business right there. The other thing that I'm seeing is we need to do 2 revolutions. And that says to me we need our argument inside of the sine function to go from 0 to 4 pi. So we need to travel 4 pi times faster. So if before, way up here, we were traveling 3 times faster when we plugged in that 3, I think I can just go ahead and throw in a 4 pi into this guy and we'll be there. Oh, I almost had it all on one page right here. So I'm kind of repeating my old guess, but bringing in some new parts here. So 2 cosine of t, negative 2 sine t is going to become x of t is 2 cosine 4 pi t. Y of t is negative 2 sine 4 pi t. I'm kind of thinking we got, and I have to state my time interval here. That's definitely a component of my parametric equation right here. So I think that this guess right here is going to get it for us. And I'm noticing that when I plug in 0 for time, I'm going to be at my appropriate starting location. When I plug in 1, my final point for time, I will have traversed a total of 4 pi in angle. That's getting thrown into my sines and cosines. That's representing our 2 revolutions. We know that that's all happening in the correct direction right there. And I'm just going to put here verify in Desmos. Because I think we've got this right. The 4 pi fixed our speed to get us 2 laps in 1 second of time right there. All right, so let's go ahead and check this guy out in Desmos. and see and feel good about ourselves here. So 2 cosine of 4 pi t, negative 2 sine of 4 pi t. And we're going to, and importantly in Desmos, we're going to only give it that time interval from 0 to 1. And we want to see if in fact we do 2 laps in that amount of time right here. So I've got here, let me pop over to Desmos. So we've got, and again, I'm going to do the same thing as I normally do here, which is, so we've got 2 cosine of 4 pi t, comma, negative 2 sine of 4 pi t. It is giving us a radius 2 circle, so that part's good. And I really don't care about this as long as it gives me the whole circle. Now I'm just going to straight up copy and paste this whole thing, but the thing I'm going to change is I'm going to change the t's to any other letter. I just pick A all the time. And I'm going to add a slider for this guy. And the super important thing here is that this slider only gets it 0 to 1. And what I want to do is I want to do this one time in the forward direction right here. So let's go ahead. And so notice here at time 0, we are starting at 2, 0. Can't I add a label to this thing? I thought that was, oh wait, is this? Can't I just do this entire thing as my label? Apparently not. Yeah, that's all I wanted. Oh, okay, cool. So we're starting at 2, 0. Oh, come on, man. And it looks like, all right, all right, all right, all right. Definitely, what's this say? Is this just to play one time? There's 1 lap completed. And here comes a boom, second lap completed right there. So we did do 2 laps in 1 unit worth of time right there. And again, this 0 to 1 wasn't really the meaningful one. That just made the graph fully appear right there. This guy going from 0 to 1, that's the one where I needed to make sure that 2 laps occurred, because this is actually my particle, not just the path that it was taking. The particle needed to do 2 laps around the path. So this is my meaningful 0 to 1 setup right there. So again, Desmos needs to be your best friend. What I very often find with all my Desmos graphs is that like stuff like this, I forget it, and then I just Google something like Desmos parametric equations, and the very first hit is like a really nicely descriptive Desmos graph that you can modify that kind of shows you a bunch of this stuff right here. So don't be afraid to Google around for things relating to Desmos that can like help you with some of this stuff right here. I really am not very good with Desmos. I just find that it's really, really easy to Google things, and it's really, really easy to share your Desmos graphs right here. So like, for example, I can click share, and it just gives you a link that will always work for exactly this graph setup that you've got right here. You can even like print it or like save it as a JPEG or something. So I'm just going to, just for the sake of doing this, I'm just going to click the copy button and come back over here into Microsoft Word. I can just kind of throw in our verification right there. So there we go. That graph is now in the notes right there. And it just gives you a link that's just going to work forever right there to take you to the Desmos graph, which is really nice. So you should be best friends with Desmos. And again, I'm just going to say it for the billionth time. Picture taking this class 50 years ago and how much harder this would have been. This Desmos link right here is like revolutionary. I mean, in the grand, think of how little time has passed for us to make such huge strides in our ability to kind of do these types of things. So let's go ahead and look at our last problem for the day. Let's go ahead and look at overlapping paths versus collisions right here. So let's consider these 2 particle trajectories over the time 0 to 2 pi. What we want to do is we want to ask, do these 2 particles ever overlap in their paths? And if they do they actually hit each other? Or are they just kind of like cycling around near each other but never actually touching each other? Or are they coming together and hitting one another right there, right? So trajectories overlapping does not mean that they hit. And in fact, there's many planets actually that have overlapping trajectories that aren't not many planets. I think that there's doesn't like Venus like swap orderings with some other planets or something like that. So I don't know. There's something like that where there's some overlapping trajectories, but not necessarily any collisions. And so let's go ahead and ask ourselves about these guys right here. So do their trajectories overlap? For this, what this kind of really means to me is I'm really not worried about any arrows. I just want to know about shapes of graph. So what shapes do these graphs take on? Well, you should notice here that our first guy right here looks sort of like a circle. Let me say particle 1, almost a circle, but radii terms are different for x and y. So it seems like my x span goes from -3 to 3, whereas my y span only goes from -2 to 2. That means that we're going to get an ellipse here, right? Just a radius that's different over time. What are we getting for particle 2? Well, particle 2 also sort of looks to me like a circle, but it looks like it's been shifted here, right? So the cosine and the sine parts say to me we're getting a circle. It just seems like this has been moved up 1 and left 3. So what I'm sort of picturing that we're going to get here, let's see if I can draw a by hand graph of this thing. Ugh. So particle 1 is going to be traveling on an ellipse. That's going to go, I'm going to mark my 4 corners of my ellipse right here. There's my 4 corners of my ellipse. -3 to 3 in the x span, -2 to 2 in the y span right here. So here's my particle 1's path. Ooh, that went really good to that last part right there. So there's particle 1. And particle 2 seems to be centered at -3, 1. And it's going to be a unit 1 circle. There. So it seems like there are 2 locations of overlap. Which means there are 2 potential collision locations. All right. And by the way, let's go verify this in Desmos because I'm right, but you shouldn't believe me about me just kind of graphing these things like this guy right here. So let's go ahead and graph these guys super quick. So our graphs were 3 sine t and 2 cosine t. So 3 sine t, 2 cos t. And notice it's only giving me part of it right here. You just need to extend this thing. I can tell that I only need to go to 2 pi because I'm dealing with sines and cosines right here. And I know that their period is 2 pi, so they'll repeat after that. Our other graph of interest was the -3 plus cosine and 1 plus sine. So -3 plus cosine and 1 plus sine. And once again, time from 0 to 1, I've got 2 functions that are periodic 2 pi, so I want 2 pi to be my upper end right there. So we're getting basically exactly that curve that I had graphed there. Mine was a little jankier, but got the exact same point across right there, so I feel good about that. So the question now is, do these actually hit each other? Or are they just going to do this type of motion right here where they're overlapping in their paths but never actually hitting? Or do they sync up and bang into each other at some point or another? Do we actually get a collision? So what's the difference between a collision and an overlap here? We should at least state that. So let's kind of state this right here. What's an overlap? Well, that's where we're going to get x1 comma y1 equals x2 comma y2 at some time. This just means that there's going to be positions on the graph that are the same for graph 1 versus graph 2, particle 1 versus particle 2. A collision, though, is a little more special than that. We need to be at the same place at the same time, not at some time. And I should, man, I'm even going to erase this and write that much, much more clearly at some time. Here, instead, we're going to need to know that x1 at, and I'm going to give a special time here, t star, y1 at t star equals x2 at t star, y2 at t star. Same location at the same time. Here, t star is the time of collision. All right, so there needs to be some special time at which at that one time across both particles, those particles are in the exact same location. So what do we need to do here? Well, it looks to me, based on this collision statement that I'm making here, is it needs to be the case that x1 of t needs to be the same as x2 of t, and y1 of t needs to be the same as y2 of t as well. That's what I got out of my collision equation right there. All right. So let's build two systems of equations and see if we can solve them. So what do we have for x1? x1 of t is 3 sine t. x2 of t, negative 3 plus cosine t. My second set of equations here is saying the y values also have to correspond. So 2 cos t equals 1 plus sine t. Now, it looks like we've got kind of a lot of options right here as far as solving goes. I'm kind of thinking to myself, I don't know. I guess the easiest thing to solve for here is either the sine on the right or the cosine on the left. I think that solving for the cosine on the left is going to be simpler since over here it'll get multiplied by 2 versus, I don't know, that's not even necessarily true. Whatever. We're just solving a system of equations. I just want to get some cosines and sines to line up right here. So let's do 3 sine t plus 3 equals cos t. And now I'm going to go ahead and plug that guy in over here. So I'm going to get 3 sine t plus 3 equals 1 plus sine t. And that's going to give me 6 sine t plus 6 equals 1 plus sine t. And that's, I'm going to subtract both these over. I'm going to get 5 sine t plus 1, oops, sorry, plus 5 equals 0. Clearly, sine t is equal to negative 1. And therefore, we should be getting that t equals sine inverse of negative 1. What angle are you at when your sine, the output from the sine function is negative 1? Sine measures vertical height on the unit circle. We're at a height of negative 1 on the unit circle, and we have done 3 pi halves rotations here. So it looks like 3 pi halves. So time of collision is 3 pi halves. But what I'm probably interested in is where is the collision? Now, it should be the case, by the way, that we should be able to plug in this into either of our equations right here. So let's do x1 of t star, y1 of t star. And that is our very first one here. So it's 3 sine t, 2 cos t. 3 sine 3 pi halves, 2 cos 3 pi halves. Sine of 3 pi halves is negative 1, so I'm going to get a negative 3. Cosine of 3 pi halves is 0, so that's good. Now, technically speaking, I am done right here, but a good thing for us to do is to verify that we didn't screw up our math anywhere, is that it better be the case that we get the exact same thing out if we checked the second particle also. So this is just this is me being a good mathematical citizen right here. I want to just do good work here. Negative 3 plus cosine, 1 plus sine. Negative 3 plus cosine, 1 plus sine. And what you can see here is this is negative 3 plus 0 is negative 3. This is 1 plus negative 1. That is 0. All right, so it looks like there were two collision candidates. Um, and so let me kind of like conclude what we saw right here. These particles experience two overlaps in trajectory, but only one will have a collision at times t equals 3 pi halves plus 2 pi k, right? It's going to keep on happening there. And note it's going to keep on happening there, right? Because these are both equations that are periodic, 2 pi at location x, y equals negative 3, 0. And as our final thing to do here then is we should go to Desmos, graph the two things, put both of their dots on them, and click the play button and see that one of the overlaps will not result in collision. One of the overlaps will result in collision. So let's go to Desmos to wrap this guy up right here. I want to graph both of these, which we've already graphed. But now I want to go ahead and add their particle components as well. So I'm going to copy and paste the first. And I'm going to change these to A. I'm going to copy and paste the second and change them also to A, because I want to be able to click play on one slider button. I want to make these colors match right here. So this was my red and this was my blue. And what I would like to do is have this time go from 0 to 2 pi. And let's go ahead and start this guy right here. So it looks like, here's the important thing. We know to expect that this collision is going to occur at negative 3, 0. So there it was right there. They hit each other right there. There's the actual collision. Now notice as we proceed a little bit further, they missed each other at that overlap and trajectory that's associated with that other upper point that's right there. So we can see the collision happen here, and we can see the miss happen right there. So we've got our full description now of the relationship between these two particles. They will in fact hit each other. They cross their paths twice, but they only hit each other once right there. So collision versus overlap. Overlap is just a purely graphical thing. Collision required our consideration of the time component to talk about that one as well. I have the rest of my arrow here. Okay. So as my closing thought for the day, let me just move this last thought down here. My last thought for the day is the same thing as my repeater thought that I've had all day. Fortunately, exploring parametric equations has gotten way more natural for all of us with the availability of Desmos. We can actually picture things that used to take people just a ton of work to work out before. Imagine investigating the following problem 50 years ago. Now, the ones today, I am positive that 50 years ago, I could have done everything that we did today without honestly too much issue. This is one right here where you're really going to see that this would have taken a mountain of work to do by hand, and this is going to be literally just as easy as anything else that we've done today. So what I would like to ask you to do as your departing problem from section 10.1 is go ahead and check out these graphs here in Desmos. I guess if I'm being formal here, I should put my functions of t in here. This will form what are referred to as Lissajous figures. I'm sure I'm slightly mispronouncing that because I don't speak French. And so go ahead and check these guys out. You should notice that there's three parameters here. You should notice that they both get a coefficient, A and B, but only one of them gets this interior n that's also associated with that guy right there. So here's what I want you to do in Desmos, and this will take you like 2 minutes. Graph this ordered pair in Desmos to graph them parametrically. You're going to add sliders for A, B, and N, but here's the one distinction that I want you to make. A and B should be able to be any real number, so you don't need to screw around with how those sliders are defined. It would be better for you, you're going to see the action of this better if you make sure that N is only an integer. So when you go to create that slider for N, and I'll show you what I mean in this A slider over here, when I click this A slider right here, it gives me an interval, but it also gives me a step size. So if I made the step size 1, then what you'll be able to see when I come back, and I don't know if you can see this in the video, but you should see little dots. This will force it to only be at integer values. That's a bad idea for this graph that we're looking at right now, but for these Lissajous curves, it's meaningful for us to only look at those integer values of n, and this is the way that you can do it, is to give it a step size of 1 and to let it vary in that way right there. I think I can just delete this, and it's good with that going back to being a continuous thing right there. So go ahead and take a look at these Lissajous curves right here. And again, this is one of those things where the whole time you should be saying to yourself, man, what if my grandpa had to figure this thing out or something like that, right? And what you're going to be able to see is a and as I'm kind of saying this paragraph right here, it should be an absolute piece of cake for you to be able to tell me exactly what A, B, and N are all controlling, and you should be able to predict exactly what any Lissajous figure looks like based on me just saying, hey, here's a Lissajous figure with A, B, and N being, 4, 6, and 19. What's it going to look like? And you should be able to say, oh, that's easy. I checked it out in Desmos. It's going to look like this. Whereas that would have taken somebody like a day's work to figure out historically here. And so feel the appreciation for Desmos. Go ahead and check out your Lissajous figures here. This is a challenge problem in our textbook in number 47, but I also literally think that the current edition of the textbook that we're using, I shouldn't say current, the version of the textbook that we're using maybe predates Desmos, and so it's maybe this actually was a challenging problem back in the day, or at least one where you'd have to graph a ton of things in your crappy TI calculator, whereas now we can produce, in a sense, thousands of different graphs essentially simultaneously with a slider bar here in Desmos. So go ahead and check out these ones here, see some interesting things, convince yourself that if I were to ask you to, in 2 sentences, tell me exactly how to know what shape we're going to get for A, B, and N, that you could be able to tell me right here. This is a very kind of an easy question right here. Only easy because you have access to Desmos, so feel that appreciation. So what we're doing in our next video is we're going to take everything that we just learned about parametric curves today, and we're going to apply like 2 semesters worth of calculus to parametric curves. We're just going to define like everything meaningful in calculus that you've ever seen. We're going to hunt for those same concepts with parametrically defined curves rather than y equals f of x curves. And that's what we're going to do in the next video. And so it's literally just going to be like walking down the list of calculus topics. Can we do derivatives? Can we do integrals? Can we find arc length? Can we find area under curves? Can we find surface area? Stuff like that. We're just going to walk on down the list and reformulate everything we've seen in the past in terms of parametric curves. It's really cool. Things work out really, really nicely. I really do like this chapter 10 stuff. So that'll be our unit this week is all parametric stuff. Our unit next week is all polar stuff. And then we're just covering chapter 11 for the rest of the class here. So that's all I've got for you guys today. I will see you for calculus with parametric curves in the next video. Have a good one.